But go ahead and see if you can draw a function that has all of those parts. I'll give you about 2 minutes. And feel free to unmute your mic if you want to ask any questions while you're trying to draw a graph that matches those descriptions. All right, so as I go to graph a function, again, I do want to make sure I graph a function so it passes like the vertical line test. I'm just going to go part by part, A, B, C, D, E, and so on, and I will try to color code it so you can kind of see where different parts are going from. For the first one, it tells me the limit as x goes to negative infinity is equal to -1. This is describing some horizontal asymptote on the left-hand side of the graph. So I know somewhere on the left-hand side of the graph, it needs to settle off at -1. Looking at B, it tells me the limit does not exist. So I know the left does not equal the right-hand side when they are approaching. The limit as x goes to -2 from the right does exist, so it either needs to end on the right at like an open or a closed circle and not an asymptote. And then it does tell me that f of -2 is 0, so it does tell me that there is a value on the graph there. I'm going to put the value there first, so f of -2 is 0. The limit when you come into the right exists, so I know that the graph is going to come in somewhere from the right, so I'll grab a portion there. But the limit overall does not exist. So I could have either a jump here, or it could be an asymptote. And I'll just kind of make a note of that. This next section, it tells me that the limit as x goes to -1 from the left is equal to the value at f of -1. Doesn't tell me what that value is, so I'm just going to pick a spot. There's my value at -1, and the limit is equal to that. But then the limit as x goes to -1 does not exist. So again, I can have another asymptote, or I can have a jump in the graph. So I'm going to go ahead and fill in everything from A through C right now. I have a horizontal asymptote at -1. It tells me the limit at -2 doesn't exist, so I'm just going to put an asymptote there. Could have just made it a jump. I have the limit as -1 from the left is existing, but the limit overall doesn't exist. And I'm just going to go ahead and just make that a jump instead of an asymptote. And it does tell me the limit as x goes to 0 exists, but f of 0 is not defined. That statement is basically describing a hole, not a jump. So I know that somewhere this graph comes up and there's a hole, but it is going to match up from the left and the right since it says the limit is existing. Then I have this next portion. The limit of 2 exists and f of 2 is defined, but the limit does not equal the value. So this is another hole, but it's going to be a hole with like a filled in circle either above or below it. And that was at 2. Doesn't matter where I put it. I'm going to put my value up here. So there's my hole. Again, I have from the left and the right is existing. It says the limit as x goes to 3 from the left is 1. So from the left is 1. It could be open or closed. And it says the limit as x goes to 3 from the right is negative 2. Could be a closed or an open circle. And then it tells me as x goes to infinity, that we're settling off at 2. So we have a horizontal asymptote, and it needs to settle off at 2. So this was my graph of f of x. Yours could look completely different, but there are, of course, it has to meet those qualifications. I don't really want to take time and have you like share your screen, but definitely if you, like I'm going to look at everyone's, but if you definitely want me to look at yours, because you think you might have some issues, then send me a remind and I'll kind of look at it for you. But are there any questions on how I came up with this, or if you wanted to ask any questions about how you maybe graphed yours? Going once, going twice. Cool. So today's topic, if you wanted to title it anything, is going to be limits analytically. When we see that word analytically in calculus, that's just another way of saying algebraically. I'm not sure if I'll finish all these today. I want you sitting in front of the screen live for the entire 40 minutes. But we'll get down as much as we can, and whatever we can't finish, then we'll just finish up tomorrow. But if you want to title your notes anything, it's going to be limits analytically. So when I'm doing limits analytically, we're going to basically fill in a flow chart. So if you want to graph this, draw this like on your own sheet of paper. I did also paste a blank flow chart in OneNote for you to reference, and one that actually is already filled in. But this is going to be the flow chart that we are going to do in kind of the order that you solve and approach limits. Excuse me. And so the first thing that we are going to do when we're solving limits is called direct substitution. Direct substitution means we are basically going to plug it in. And when you plug in the number, there's basically going to be 4 different things that can happen. And we're going to talk about some of these today. Some of them we're going to save for Friday, Monday, and Tuesday. But basically 4 cases can happen when you plug in a value. And so a limit question, let's look at an example. Here's one function f of x. So I do have a rational function. And we want to figure out different things that can happen. So if I want to find what the limit as x is approaching 0 of f of x, the limit as x approaches -3 of f of x, and the limit as x goes to 1 of f of x, the first thing you always do is direct substitution. So go ahead for me and just do direct substitution by plugging it in. So literally for this first one, we have 0 minus 1 over 0 squared plus 2 times 0 minus 3. Probably don't have to show all that work, but go ahead and do direct substitution and simplify it to kind of see what you get for each of those. And so these are the different things that I get when we plug in direct substitution. Only one of these actually has the final answer. So in this first one, I have the limit as x goes to 0. We plug in 0 and we get a real number 1/3. Those are the ones you're going to like. When you get a real number, that means you are done, and that is your final answer. So the limit as x goes to 0 for this particular function 1/3 is, excuse me, to 0 is 1/3. So on the graph, if you were to graph this, you would see on the left-hand side and the right-hand side of 0, it would be approaching the y value of 1/3. The second one, going at -3, you plug in -3 and we get -4/0. Well, in math, if I have -4/0, what does that mean or represent? Feel free to unmute your mic and take a guess.
It's undefined.
It's undefined. So this value, a number over 0, is undefined. What do you think the limit's going to be when we say undefined? Take another guess. Someone said, I think I was talking over you. D&E does not exist. So when the number is undefined, we're going to say the limit does not exist. This last one is where we're going to have some issues. So 0 divided by 0 in math means like nothing. It's not undefined. It's not 1. It is something that we call an indeterminate form. For now, I'm going to say it's something that we're going to have to keep going and try something else. We don't know the answer yet. 0/0 is not undefined. It's not a number. It's going to be your sign that you have to keep going. The first one and the second one, those are ones you like. We know what real numbers are. We know a number divided by 0 is undefined, so it's going to be D&E. The problems you don't like are going to be when you have 0/0. And surprise in calculus, most problems are written so you do have a keep going there. I do want to kind of show you some other things that are happening in this problem. So this is a rational function. If we wanted to graph it, good use of prereq skills, we know we could factor this out. And so I have this when I factor it. And so when we're looking at that factored version of the rational expression, what is the vertical asymptote for that rational expression? Which factor does not cancel out? The x plus 3. So we have the vertical asymptote at x equals -3, which makes sense when we plugged it in and got a number over 0, because we know that when limits approach an asymptote and goes towards infinity, that's an example of saying does not exist. What's happening at this factor, x minus 1 gives you x equals 1. What feature is showing up on the graph there?
A hole.
A hole. And so in this case, we know rational functions, those are easy to deal with. It's a hole. So this third example, we want a way to kind of figure out where that hole is going to be located at. Some other ways that we can do direct substitution is when we have piecewise functions. So when we're looking at this, I have the limit as x goes to 2. Remember, the minus sign means from the left. The plus sign means you're coming in from the right-hand side. And then when you just see x goes to 2, you have to consider it for both sides. Well, this is a piecewise function. So we know a piecewise function, if we were to graph it, we have one graph existing on, for the 3x plus 1 is only existing when x is less than 2, not including 2. And when I have x squared minus 3, this portion of the graph is only existing when x is greater than or equal to 2. So if we want to find the limit as x goes to 2 from the left, on the left side of 2, which portion of the piecewise function are we going to want to use? If we're coming in at 2 from the left.
The first one?
The first one. So we think about the number line. 2's here. When we're less than 2, we're on the left-hand side. So I would just plug it into the first one. 3 times 2, 6, minus 1 is 5. So then likewise, if I want to find the limit as you're coming into 2 from the right-hand side, we're going to use the other one, lugging it in. 2 squared minus 3. 2 squared is 4. 4 minus 3 is 1. So then that does bring us to this last one. What do we know the limit as x goes to 2 is going to be, and why? If someone wants to take a guess at that.
It won't exist
And why are we saying it won't exist?
because coming from the right and left, it's different.
Because coming from the right and left is different. So we can say D and E. If this is the AP exam, we want to make sure we are used to using like formal math language if it asks for a reason. And it's going to be D and E because the limit as x goes to 2 from the left of the function is not equal to the limit as x goes to 2 from the right of that function. So I won't always ask you to give a reason or justify it, but you do need to get used to, especially as we get deeper and deeper in this course, being able to like justify your answer using proper math notation. Any questions so far? All right. So now some other things to consider. Some basic math in some ways. I have like a bunch of fractions here, basically a bunch of divisions here. I want to kind of talk about like what that means and like what it would be equal to. Limits are weird because you're often dealing with like infinities, or you're dealing with like very, very small numbers, are dealing with very, very, very large numbers. So I do want to kind of think about these different things that we have and what they mean. I do realize I repeated one of them on here. So let's kind of think about what we have. I'm going to do the kind of go row by row instead of column, so row by row. This first one, if you have 0 divided by anything, what is that always going to be equal to? Zero. 0 divided by anything is 0. And the one that's cited in blue, if you have infinity divided by anything, so in your head, we're going to get very conceptual. Infinity, just kind of imagine that's like the biggest number you can think of. So the biggest number you can think of divided by anything is still going to be what? A big or a small number?
Infinity.
Is going to be infinity. So we have infinity divided by anything, like infinity is the most massive number idea that exists. Infinity divided by anything is still going to give you infinity. Next row, if I have anything divided by 0, kind of already touched on this today, what is going to be anything divided by 0?
Undefined.
Undefined. So that's going to be a limit that is D and E. Moving across, think about this one. What would be anything divided by a really huge number? So kind of start thinking about fractions where the denominator is super, super, super big. What would anything divided by infinity become?
One over infinity.
So we have 1 over infinity. Let's just kind of think of some numbers. Maybe you have your phone and can look at the decimals. Anything, I'm just going to pick the number. Let's just do like 5. So maybe in your calculator, do like 5 divided by 10, 5 divided by 100, 5 divided by 1,000, 5 divided by as many zeros as you can fit. So again, limits are talking about what you're approaching. So we want to have this idea of what would be anything divided by a super, super massive number. What does that look like it's approaching?
0.
0. So basically we're thinking about this like an asymptote. If you keep dividing by bigger and bigger numbers, you're going to get closer and closer and closer to 0. So I'm not going to really say equal, but it's going to be approaching 0, which is going to be nice to talk about in terms of the context of limits. And then this last one, if I have anything divided by itself in math, what is that going to give you?
1.
1. That's the easy one. And then that brings me to these last two that I kind of put in bold. 0 divided by 0, again, that's not the same thing as saying anything divided by itself is not equal to 1. Same thing for infinity divided by infinity, and I'm about to kind of drift off into some weird math theory land. So like infinity is the biggest kind of value, it's infinite. One thing we're going to see with limits is like sometimes like two infinities can be the same, and sometimes we have like some infinities that are bigger than other infinities. So we're going to consider these last two cases to be our indeterminate forms. There's more indeterminate forms in math besides 0 over 0 and infinity over infinity. For example, like 1 to the infinity is indeterminate, 0 to the infinity is indeterminate, and infinity minus infinity is indeterminate. So we have lots of these things called indeterminate forms in math, and that's just because mathematically it doesn't make sense to have nothing and divide it by 0. Same thing with infinity, since it's not really a number, you can't do basic algebra with it. So it doesn't like break rules of math, but we can't deal with it like we would a normal number. And that's really where the tricky part of limits is going to come into play. Any questions so far? All right. So back to that flow chart. So I told you when you plugged in something, 4 things can happen. That first case is going to be the ones that you like, and we saw that in the first example we did. When you plug something in and you get a real number, you are happy because that is your answer, and you don't have to do anything else. Another one that you're going to be happy with is when you have a number divided by 0, because a number divided by 0 is always going to be d and e. That is an undefined value, so your limit is going to be d and e. Where we're going to start having a little bit more work to do is going to be those last 2 boxes. The ones I have in yellow is when you have 0 over 0 or infinity over infinity. You're going to keep going, and notice that that does branch off into kind of 4 different things. The first one we're going to look at today is algebra. The other 3 are going to be things that we look at Friday and then even next week. But we're going to focus on the algebra today. And I do have down here on the bottom, there are some other indeterminate forms. The only one we have in BC calculus is going to be infinity minus infinity. Again, there are a lot of other indeterminate forms in the field of mathematics, but they're not required as part of this class or this curriculum. So frankly, I'm just not going to cover them, but just know that there are some other ones that exist. We're going to mostly focus on the ones that are 0 over 0 or infinity over infinity. But I'll give you a chance to copy that down if you need it or want it, and then we'll look at a few examples. And while people are copying that down, does anyone have any questions they want to ask? Is anyone still copying that chart down before I change the slide? All right. So things that we can do when we are filling in that chart. So there's algebra, and there's 3, or really 2 main things that you can do. The first one is the one that we saw with rational functions. You might want to factor and cancel. That is one option that you can do, and that's often the easiest one if you have like polynomials and things like that. The second option we have is rationalize. You'll often do this one if you see square roots in a limit. And then the last one y'all are really going to love I'm just going to call it like other algebra. Typically the other algebra with the goal of simplifying. So those are the ones that we're going to kind of start with today, and we'll kind of see where that takes us, and then we might do some more examples or we might finish it tomorrow. So the first example that we're going to look at is going to be a factor and cancel one. And so this was the example that we already did. When we did direct substitution, so you always want to try direct substitution first. You don't have to show your work for that one, but when we did do direct substitution, so I'm going to put this in a thought bubble because it's kind of happening inside my head. Plugging in 1, 1 minus 1 is 0, and then I had 1 plus 2, which is 3, minus 3 is 0. So we know that this is an issue where we need to keep going. So we want to get used to kind of making decisions. When I look at this one, I see I have polynomials, so that would be my clue that I want to factor and cancel. So let's go ahead and factor and cancel. Make sure you write the word LIM the limit every single time when you're showing your work until you actually take the limit. So I have the limit of x minus 1 over, and we can factor the denominator. So I have x and x again, 3, 1. Canceling this out, the x minus 1's cancel, and we are left with the limit as x goes to 1 of 1 over x plus 3. Are we now able to do direct substitution? Yes, we've cleared out the issue of getting the 0 over 0. So now we can do direct sub. And by doing direct sub, we have 1 over 1 plus 3, which is equal to 1/4. So the limit as x goes to 1 is 1/4 for that function. What's actually happening is there is a hole there. And so like on the graph, this graph actually looks something like this. On the graph at x equals 1, there is a hole. So you didn't need to know what the graph looks like. I do because I've been doing this a while. But we know that at the value of 1, there is a y value of 1/4 where there is a hole in the graph. So that's going to be the first type of example you have. When you have 0 over 0, keep going. Always try direct substitution first. You don't want to waste your time and like factor and cancel when you didn't have an indeterminate case to begin with. But when you have 0 over 0, factor, cancel, and then do direct sub. Questions? All right. Go ahead and try this one for me. Again, you always want to do direct substitution first. And it's a prereq skill, but if you need the reminder, that would be how you factor a difference of 2 cubes. So looking at this one, we do have direct substitution. When I go through and do my direct substitution, we end up with 4 cubed minus 64, which is 0, 4 minus 4, which is 0. Sad because we have to actually do some work. So these are polynomials. So big clue we want to do is factor and cancel. So I have x minus 4, same sign, opposite sign, always positive. All over x minus 4. By factoring, we've taken care of the issue of having the 0 over 0. And now I can go ahead and do my direct substitution. So I have 4 squared plus 4 times 4 plus 16. Do you want to remind you of my class? You can leave an answer like that. Doesn't offend me. It might look ugly to you. Or you can simplify it to just be 48. But both answers will be the same because they are equivalent to me and College Board. Questions on that? All right, let's squeeze in one more example and then I'll finish here and we'll pick up tomorrow. We can also rationalize. So rationalizing is going to be the example when you typically see a square root. Again, always try direct substitution first. This is pretty easy to check direct sub because you have 4 minus 4, which is 0. 2 minus the square root of 4, 2 minus 2, which is 0. So we do need to do something. We do need to rationalize. Sometimes you rationalize the numerator, sometimes you rationalize the denominator. Does anyone remember how we rationalize an expression like this?
You multiply by the conjugate.
You multiply by the conjugate. So I'm looking in the denominator. I'm going to multiply by the conjugate in the top and the bottom because we're really just multiplying by 1. Some hints I will say. You only need to factor the part that you're rationalizing. So only like FOIL out and multiply the part that had the square root. So in this case, I'm going to FOIL together the denominator. I'm going to leave the numerator separated because the goal is if you do this correctly, something should cancel out. So rationalizing, I have the limits as x goes to 4. I'm going to leave the numerator as is because it did not originally have a square root in it. I am going to go ahead and FOIL together the denominator. So I have first, which is 4, the outer, and then inner, and last. Negative square root of x times the positive square root of x is going to be just plus, excuse me, not plus, but minus x. Simplifying, hopefully you can kind of see where this is going. Most of you could probably skip that middle step I just wrote down and jump straight to this step. We have 4 minus x's, something cancel. If you rationalize and something doesn't cancel, then you probably did something wrong. So then now we can go ahead and do our direct substitution. 2 plus the square root of 4. You can leave your answer like that, or you can simplify and say 4. This graph also has a hole at x is equal to 4. It's a different type of rational expression, but by rationalizing, we're able to find that hole and find where it's located at. Questions there? All right, so 2 minutes. I'm still not used to these 40-minute periods. I'm probably going to have to adjust my calendar a little bit, which is fine. So my final instruction I want to give you, so tomorrow is Friday. So please make sure on Friday you have turned in that prereq assignment, that prereq homework number 0. Also, if you haven't signed up for the My AP Classroom, please do that as well. So homework you have, I did post it into Teams just instead of doing it on the slide, so you always have access to it. So you have the homework 0, which is due Friday, tomorrow at 2 p.m. Some of you have started on homework 1, and I saw that. There is a homework 2, like I haven't finished this topic, but if you are feeling like extra eager, then you can start homework 2, but of course I just care about getting homework 1 or 0 done first. So that brings us to the end of class. You can go ahead and exit, and I'll see y'all tomorrow, and we'll kind of regroup. And I'll probably send it out a different calendar to adjust a little bit. If you need to hang back a little bit and ask any questions or anything you want to clarify as people leave, you're more than welcome to do that as well. But other than that, I will talk to you tomorrow. Y'all can go ahead and sign out and get ready for 4th period unless you want to hang back to ask any questions. But see y'all.
Mr. Brown, do we have any homework? Are we supposed to start working on the
You can
limits?
start homework 2 if you're there.
Okay.
Like I would first obviously do homework 0
Yeah.
and then homework 1. And if you can, like, you could probably do most of homework 2 right now if you wanted to get ahead, but we'll finish the notes up tomorrow. I kind of overestimated how much I could get done in a 40-minute period, which is fine.
Thank you. See you tomorrow.
See ya.